Hi guys, so this is the second lesson on Pythagoras. If you watched the introductory Pythagoras kind of recap, then you will have seen me go through these two examples in the notes. One where we are finding the longer side in a standard right angled triangle. That's where we use c squared equals a squared plus b squared, this first formula here. And then secondly, when we have a smaller side that's missing, we actually just rearrange the formula. A squared equals c squared minus b squared. Now, if you did the recap video, you will have worked through that with me. If you didn't, if you didn't do that video, you should still remember this from working on this previously, and you should be able to do these two examples yourself, no problem. So we're going to move on to the National 5 level Pythagoras work now. Now, again, I'm currently waiting a PCR result. I have pretty blocked nose and a bit of a sore throat, so apologies in advance for all of that. But anyway, so at National 5 level, we have basically three different kind of more complex situations where Pythagoras is applied. The first is in a three-dimensional shape, like a cuboid, which you see below. We're about to deal with that first of all. Secondly, it says here in diagrams involving circles. We're not actually going to look at that at the moment. In this unit, we kind of revisit Pythagoras later on, so we'll do this second bullet point in a future unit. And the third thing, which we are going to do in this unit, is using the converse of Pythagoras, and we'll deal with that in a future video. So this example one, we have to find the length of the space diagonal AB. Now, space diagonal is all that is the line connecting A and B, and it's going through the space inside the three-dimensional shape. Okay, so that's this dotted line, represented by this dotted line from A to B. That's all that kind of phrase means. Now, that's our end goal, is to find the length of that line. So to find the length of that line, I can use Pythagoras by connecting a right-angled triangle between A and B, and where this sort of right angle is drawn down the bottom right here. So if I kind of highlight that, those three sides, we've got A to B there. You've got this kind of height, if you like, 12 centimetres there, and that along the bottom, that is called a face diagonal. Now, the difference between a space diagonal and a face diagonal is the face diagonal is going along one of the faces of the three-dimensional shape. So if we know that side along the bottom, we can use it with the 12, use Pythagoras theorem to get AB. Now, the issue is, obviously, we don't know that side, that face diagonal along the bottom. But what we do have is we have these other two sides of that kind of bottom face. We have from A to this corner is 8 centimetres. And I'll highlight that in a different colour. We have from that corner to the right-hand side is 9 centimetres, and we can actually connect that those two sides there, and what we're going to have is actually a right-angled triangle, another right-angled triangle. So if you imagine this as a box, this here would obviously be a right angle because it's a 90-degree corner, because it's a cuboid, a rectangle, a square on the bottom there. So essentially these problems, all we're doing is using Pythagoras twice. We're going to use Pythagoras first of all to get this face diagonal here. So we're going to use the green triangle first to get this side along the bottom. We're then going to use that side in our red triangle to get this final goal of AB. So what we're going to do is, first of all, draw out the green triangle. I'm actually going to draw it in green just so you can have a visual representation of which one we're doing. You don't have to draw it in a colour, but just know which one we're doing. So we've got the first triangle, right angle triangle, which imagine I've just kind of pulled that out from that bottom face. That means we're going to have this 9 centimetres along the bottom there. 8 centimetres is going to be there, and then the missing side is the longest side. It's across on the right angle, so we're going to call that C. And then we can call the other two A and B, whichever we like. So this is nothing new, really. All we're doing at this point is using Pythagoras theorem to calculate this initial side C. So we'll start with Pythagoras theorem for a longer side, which is C squared equals A squared plus B squared. And we're just going to go through it the same way we did in the examples at the top of the page. So C is equal to 9 squared plus 8 squared, and then, C squared is equal to 9 squared plus 8 squared, so C is equal to Remember, we do the square root of that whole thing, so we only have to put one thing in our calculator. Just saves time, saves making mistakes, only have to visit a calculator once. So if you now put that in with me, remember, if you are using a white and black calculator, you're going to have to put this, what's underneath the square root, in a bracket. If you've got a Casio calculator, it does that automatically for you. So it's the square root of 9 squared plus 8 squared. That's given me an answer of 12.041, which we can approximate that to 12.0 centimetres. Okay, so we're halfway done, essentially. We can now mark on onto our diagram that this face diagonal along the bottom is 12 centimetres. So what I now am able to do is I now have 2 out of the 3 sides in my red triangle, which is what I need. I need at least 2 of the 3 sides in order to find the third. So I can now draw my other triangle, which I'll do over here, not very neatly. So we have 12 centimetres along the bottom, we have 12 centimetres up here, and again, the missing side is across on the right angle, which means it's the longest side, so we're going to call that C. And it's okay to call it, C again. You don't have to change the letter. We don't really need to call it C1 and C2, just C is fine, which means 12 and 12 are the 2 smaller sides, which means they are A and B. So literally exact same process, just slightly different numbers, and then we're just repeating Pythagoras' theorem in order to get this this final side AB. Well, I suppose we could actually call that, rather than calling it C, we could call it AB, because that's what we've been asked to find in the diagram. So AB squared is equal to A squared plus CB squared. So AB squared is equal to 12 squared plus 12 squared. So then we get the length of this line, AB, is equal to the square root of the same thing, 12 squared plus 12 squared, same as before. And then it's just a case of putting that into your calculator carefully. Square root, 12 squared plus 12 squared. So I'm getting an answer of 16.970 which we can approximate to 17.0 if we're being proper centimetres. That's to 1 decimal place, to 3 significant figures. It's to 1 decimal place. Okay, so these 3-dimensional shapes, it's just usually a case of using Pythagoras twice. So just identifying what the right angle triangle is. Are you looking for a longer side? Usually you will be looking for, if that diagonal along the bottom of a cuboid, it's always going to be the longer side. So usually it is, but not always. So what I'd like you all to do now is you should have a worksheet, a 3-dimensional Pythagoras worksheet there, which has 4 questions on it. Has the answers on the bottom. I'd just like you to work. These ones are kind of split up more. Find this line first, then this line. So it's kind of split up for you. The two bits or 3 bits are kind of split up into sort of A, B's and C's. So if you can do that worksheet and answers at the bottom, you can check your answers.